Okay, so welcome to this third slot of the protection session. I'm Fabiola Cavaliere, and you might have been already yesterday in the first two slots of the protection session. So you maybe know already that protection is a project funded by the European Union in the context of the Marie Curie program. And it is based on 15 projects which link universities with industries, European industries. So I'm one of the PhD student from this project, and today the first three speakers will be also from the same project. Totally, we will have 5 talks. So I guess we can start with the first speaker. He is Meghed Shaban with the presentation with the title Isogeometric Analysis of the UV irradiation curing process in additive manufacturing. So enjoy the talk. Feel free to ask the questions in the chat as always.
Hello, everybody. My name is Meghed Shaban. I'm a PhD student at Eindhoven University of Technology in Department of Mechanical Engineering. Today, I would like to present about isogeometric analysis of the ultraviolet irradiation curing process in additive manufacturing. This is a joint project between Eindhoven University of Technology, Canon Production Printing Company in the Netherlands, and University of Bavaria in Italy. As an outline, first I will give a brief introduction. Second, I will be talking about the physical and mathematical framework, modeling the illumination and the photopolymerization. Then I will be talking about the simulation results and its discussions. Finally, I will give conclusions, point out the complication which we are currently facing and our future work. Additive manufacturing stereolithography process works by focusing an ultraviolet laser on a vat of photopolymer resin. With the help of computerized manufacturing, the ultraviolet laser is used to draw pre-programmed design or shape onto the surface of the photopolymer. Photopolymers are sensitive to ultraviolet light, so the resin is photochemically solidified and forms a single layer of desired 3D object. This technique is called photopolymerization, and it has many industrial applications. The typical reactants in the photopolymerization reaction are the initiator molecules, free radicals generated by initiators, polymer chains, monomers, oxygen, and solvent. Most of photopolymerization resins are acrylate-based, which implies kinetics of the free radical polymerization type. And in general, successful photopolymerization processes are based on 3 primary reaction mechanisms. These mechanisms are initiation, propagation, and termination. Typical photopolymerization process can be shown by Goodner scheme, and based on this scheme, we build our photopolymerization model. The relation between illumination and photopolymerization is still very incomplete. Currently, there are no simulation techniques which account for the full photopolymerization process, and only scan simulation tools are available. So our goal is to advance modeling and simulation technique of photopolymerization process, in particular, to study the illumination effect on the different components of ultraviolet curved resins. I would like to disclaim presenting the isogeometric analysis part. We envisage developing a Maxwell model for illumination based on isogeometric analysis, but that's still under development. The light intensity through the resin sample can be described in 2 ways, based on if the solvent resin either has inclusion or not. In the case of homogeneous solvent without inclusion, the decrease in the light intensity throughout the sample is calculated using the Beer-Lambert law, which is in equation 1. This law considering just the incident light, the light dips, concentration, and molar absorptivity of the photoinitiators. The species balances contain 3 terms, which are accumulation, diffusion, generation or consumption by reaction as shown in equation 5. Based on the photopolymerization scheme which showed in the introductory part of this presentation, we can model photopolymerization process by the reaction diffusion equation as shown here. We connected the light intensity by the rate of consumption of initiator, which is the last term in equation 6 and the third term in equation 7, where E dash is the energy per mole of photons. In the polymerization sample, heat can be generated in 2 ways, either the exothermic polymerization reaction or by light absorption from the photoinitiators or its decomposition products. Most monomers and polymers tend to be transparent in the ultraviolet wavelengths and therefore don't generate heat via absorption. The species balance must incorporate heat transfer throughout the film, So the energy balance equation can be derived as the equation 11. In the model implementation, we considered the monomer is 2-hydroxyl misacrylate, which has an industrial name called HEMA, and solvent values for glycerin solvent. So we have a hemaglycerin system forms a homogeneous solvent in 1 mm 6 square sample with actual reaction coefficients as shown here. Here is the simulation of photopolymerization process model we built. The results show the concentration of initiator, radical, monomers, polymer, inhibitor, and temperature distribution. The results are reasonable, and we can notice exothermic polymerization reaction in the temperature distribution figure for the sample. Something that we noticed for the actual values of reaction coefficients, you get a very fast reaction and a very slow diffusion. As a result of that, you have a very fast initial dynamics related to the reaction process, while getting a stationary state is only very slow. And while doing computations, we notice that if you take a time step that is relatively large, you will immediately be running into problems with Newton conversion due to the fast reaction dynamics. We have developed and implemented a 6-field model for photopolymerization process with a temperature effect. This model allows light intensity, temperature, and species concentration to vary across the thickness of photopolymerized film. And the fundamental complication we are currently facing is a sharp reaction fronts and fast nonlinear reaction with a slow diffusion. In our future work, we are going to study polymerization conversion rate of this model and compare it with the experimental ones. This model can be extended for heterogeneous solvent or hemaglycerin system with inclusions. This means we have to take a light scattering into account. So we have to model the illumination using Maxwell equations. Then isogeometric analysis will be used to have a precise results in this case. This work is funded by the European Union Horizon 2020 Research and Innovation Program under Marie Skłodowska-Curie Protection Project. Thank you for your interest and attention. Please let me know if you have any questions or comments.
So thanks, Megat, for your presentation. As he said, if you have any questions, please just write it down in the chat. So now let's see. The next speaker is Ahmed Sherif. He's also from the ProTechTion project. He's from the École Centrale de Nantes and Instituto Superior Técnico de Lisbona. And this work is in collaboration with the company Numeca. The title of this presentation is Divergence-Free Extended Hybridizable Discontinuous Galerkin Method for Laminar Incompressible Two-Phase Flow. So go ahead.
Hello everyone, my name is Ahmed Sherif and I'm going to talk about high-order discretization technique for laminar incompressible two-phase flow applications. In particular, this method that I'm going to present satisfies the divergence-free condition. The presentation is going to go as follows, where the motivation of this work is simulations of two-phase flows like the ones involved in, for example, simulation of waterfalls or simulation of sea waves. We're interested in laminar incompressible two-phase flow. Second, this is going to be a spatial discretization technique using high-order HDG. One more thing that is a main focus of this project is the use of a single unfitted background mesh that is going to be fixed throughout the whole simulation, and that to avoid remeshing in each time step. And for this, we use the concepts of extended FEM to resolve local discontinuities. We solve the momentum and mass conservation equations. Since we're solving a two-phase flow, so therefore the material property, the viscosity or the kinematic viscosity is discontinuous across the interface. So in this development, we focus on the use of a formulation that satisfies the divergence-free condition of the incompressible Navier-Stokes equation to the level of machine accuracy. For HDG, there are two types of problems usually: the local problems that are solved in the elements, and global problem that is solved on the edges that are shown in blue. For this particular example, if the interface is shown like this, that means that it will cut through some elements that are going to be shown in red here. So those elements we refer to as cut elements. So as I said before, there are two sets of problems: the local problems and the global problems. The way how it goes is that we solve the global problem to get global variables, the global variables which are the traces of the velocity and the pressure, and then we go to the local problems to solve them to get the velocity and pressure. There are some things to note in this method that are unique to this method, is that here we introduced not only the traces between the elements, but we also introduced the traces of the velocity and the pressure on the interface. And this is made to ensure to enforce the continuity or jump conditions across the interface. And since we're using a fixed mesh throughout the simulation, then we're going to use the concepts of extended finite elements to approximate the solution in cut elements and faces. And this is done using Heaviside enriching polynomials. One important aspect as well for the XFEM or XHDG is the generation of integration quadratures in the cut elements. And for this, we use the open source code Algoym that is developed by Robert Seib. I'm going only to show one example where I solved only Stokes equation, so without convection, and the interface is fixed, and the exact solution for this problem is known. And as you can see here, I've solved this using a second order polynomial and third order polynomial for the velocity on 4 meshes of quadrilaterals, and you can see here in this table the maximum pointwise divergence of the velocity throughout the whole mesh. So it's nearly 0. And here I'm also showing the convergence rates, and as you can see here, optimal convergence rates were achieved, m+1 for the velocity. I've done it again, the same example exactly, only with the exact pressure that is discontinuous across the same interface. And you can see here how the numerical pressure is represented accurately. Here we showed the divergence-free XDG method, XHDG method for two-phase incompressible Navier-Stokes equation. It is done for the first time. Optimal convergence rate were achieved for 2D straight interface example. And as a future work, I'm going to implement this for the full Navier-Stokes equation, taking into account the nonlinearity coming from the convection term, and also extend to the 3D implementation, which are mostly done.
Okay, thanks, Ahmed, for this very nice presentation. Let's continue with the next speaker, who is Gabriel Valdés Alonso. He's from the École Centrale de Nantes, UPC Barcelona, and this project is in cooperation with the company Faurecia. And the title of the presentation is Data-Driven Identification for Linear Viscoelastic Materials.
Hello everyone, I'm Gabriel Valdés Alonso, and I will speak about data-driven identification and its application to viscoelastic materials. In computational mechanics, we have always relied on a combination of physical laws and material laws to solve boundary value problems. We use this concept inside of solvers, where the most popular one is the finite elements method that gives us as a result the displacement in the nodes, which in turn we use to obtain strain and stresses. The problem in this approach lies in the definition of the material loss, where typically we use models that are chosen in an arbitrary fashion, which in turn introduces bias in the model. One of the solutions to this problem was proposed by Kirchhoff and Ortiz, where they completely replaced the material law for a database of strain and stresses, which are used in a solver that is now known as the data-driven computational mechanics, which provides us with the same results, just in a model-less calculation. Data-driven identification is a method that is based in this idea, but now we put the focus on finding the material law by obtaining the previously mentioned strain and stress database. We focus on obtainable variables such as the displacement, the force, and the mesh properties of a sample. This can be obtained through imaging techniques that allows us to have X-different snapshots of a deformed sample. We also rely on the same physical principles of compatibility and equilibrium that we now input as constraints to solve a minimization problem. In the equation, we try to minimize a distance in the space formed by the strain and the stresses with the help of an energy norm. This space we call the phase space. As a result, we obtain the database of points independent of X that samples the material behavior. But we also obtain an estimation of the stresses in each deformed state, which is a property that we cannot always obtain in real-life testing. So this previous approach was conceived for elastic materials, where each stress is unique to a strain. However, in the case of linear viscoelastic materials, we have that stress is also dependent on the past strains. So to account for the history of strains, we extend the phase space. Each of our previous X deformed states are now steps in time, and the minimization problem includes the history by including all these steps in the energy norm, so we effectively increase the dimensionality of the problem. As a result, we obtain again an estimation of the stresses in each step, as well as the database of point independent of time that samples the problem. In the figure, you can see the results we have obtained. In here, each point in the curve represents the amount of stress estimation that have an error lower than the value represented in the x-axis. By applying the DI for elastic materials in a viscoelastic sample, we obtain good results that improve when we extend our phase space to include past strains. This can see because we have now steeper curves. If we increase the amount of past steps, we obtain better results, which can be explained by the fact that we are completing the missing information for the computation of stresses. The amount of past steps is a parameter that we need to choose properly. The more steps we add, we have a better accuracy, but we also increase the dimensionality, which at a certain point can be detrimental for the estimation. Another point to consider is the fact that increasing the dimensions slows the algorithm because of the amount of computations that are needed to be performed in each iteration. The results already shown can be improved by the use of filtering techniques such as the principal component analysis, which is a statistical technique that finds a set of vectors that fits the data in the best direction. It depends on a technique called the singular value decomposition, which is used to decompose a matrix in three different ones. One matrix S that represents the singular values, which are equivalent to the eigenvalues of a square matrix, and two matrices U and V, which are called the singular vectors, and they form spaces associated to each dimension of the matrix. PCA is done by performing singular value decomposition on a covariance matrix C that we obtain from the data with this relation. The principal components Z form a feature space that can be reduced to a chosen amount of dimensions by selecting how many singular vectors we are going to use. And if we perform the inverse process with these reduced dimensions, we obtain again our recomposed data matrix with some loss of information that typically correspond to noise in the samples. In here we can see that after using PCA in our results, we obtain an improved error curve, but this is much more notorious when we use more steps. This improvement can be attributed to the unnecessary information being removed from the data, leaving us with clearer and better estimation of the stresses. So after all this, here's a summary of the three main points to retain from this presentation. DDI is a method that comes as an answer to the need of unbiased definition of material loss. It was originally designed for elastic materials, but it has since been extended to other types. In here, we proved that we can improve the results in linear viscoelastic samples by extending the definition of the phase space. And finally, if we complement DDI with filtering techniques of the types of PCA, we can improve the results further by removing noise from the samples. So thank you very much for your attention.
Thank you, Gabriel, for your nice presentation. So now let's go to the next speaker. I see you're already writing questions in the chat. We will discuss it later in the live discussion. So now it's the presentation from Philippe Edel, is from the French Aerospace Lab and Sorbonne Université in Paris. The title of this presentation is Reduced Basis Method for Frequency Sweeps with Integral Equations using Locally Adaptive Kernel Approximation.
Hello everyone, I am Philippe Edel from UNERA, the French Aerospace Lab. Today I would like to present my ongoing work with François-Xavier Roux, who is also from UNERA, and Professor Yvon Madet from Sorbonne Université. In this work, we consider an integral equation that is successively solved under variation of the wave number in a given window. Typical applications are in electromagnetics and in acoustics. Formally, the problem consists in solving the following parametrized linear equation, where the parameter mu denotes the wave number. This problem is known as the frequency sweep problem. Here, A of mu denotes the integral operator that is usually complex, unsymmetrical, and fully populated. And on top of that, this operator is also non-affine. This is an issue because applying the reduced basis method in this context will require building an affine approximation. In this presentation, I will essentially propose a new kind of affine approximation based on the concept of local adaptivity. And I will show how this new kind of approximation can be used to drive a reduced basis method that's well adapted for solving our frequency sweep problem. As always, in locally adaptive strategies, we first choose an integer q. We then select j wave numbers as shown. When considering an arbitrary wave number mu, the idea is to look for the q nearest points. It turns out that there always exists an integer k such that the smallest among these q points is mu k. Thus, each mu is mapped to an integer k, and we say that mu belongs to the subdomain dk. We now approximate our operator a of mu by a linear combination of a at these q nearest points. I'm now going to explain how this local affine approximation can be used to drive a reduced basis method that's well adapted to our frequency sweep problem. The offline stage relies on the domain decomposition of our frequency window. We begin with the first subdomain k equals 1 by constructing the q operators that are involved in the local affine approximation that's valid over the first subdomain d1. Once this is done, we can perform a local greedy loop in order to build a reduced basis satisfying the desired level of accuracy over the first subdomain. We then move to the second subdomain, k equals 2. We just need one operator assembly in order to have the q operators involved in the local affine approximation over this subdomain. As before, we can perform a local greedy algorithm over the subdomain, but rather than starting back from scratch, we now enrich the existing reduced basis until the prescribed tolerance is reached. And we proceed in this way until all subdomains have been dealt with. Let me briefly comment on the virtues of this offline strategy. To start with, the offline memory requirements will never exceed q operators simultaneously in memory. This is very interesting because each operator is a complex, unsymmetrical, and fully populated operator due to its integral nature, and this remains absolutely relevant when compression is used, typically when the operator is an H matrix. Next, we note that the overall number of operators that need to be assembled throughout the offline stage is considerably reduced compared to previous approaches. Here are some results obtained with the double layer integral operator. Above in blue, we show the 20 wave numbers selected using a locally adaptive strategy, and below in purple, we show the 34 wave numbers selected using the element-wise or HP approach, both for achieving the same level of accuracy. Finally, the last virtue is that the integer q controls the online complexity of the reduced basis method. To finish with, let me show you some numerical results on a Helmholtz equation solved using the double layer potential. This is an academic problem on the unit sphere. Q has been set to 7, and we found 14 subdomains. On this figure, we have plotted the size of the reduced basis throughout the frequency sweep to reach the prescribed tolerance 10-2 on the reduced basis approximation error. As we can see here, the reduced basis is progressively enriched as we move from subdomain to subdomain to finally reach a maximal size of 16. On this next figure, we show the wave numbers at which the solutions of the integral equation have been computed to serve as basis functions. For more details, I invite you to read the short paper. Also, feel free to ask me any question. And for now, I thank you for your attention.
Very nice presentation, Philip. Is open to questions, as he said, so feel free to write it down in the chat. And now we go to the very last presentation of this session. This is a presentation from Fredrik Larsson. We all know he's from Chalmers University in Gothenburg. And the title of this presentation is Efficient Computation of Viscoplasticity Based on Numerical Model Reduction with Error Control.
My name is Fredrik Larsson, and I want to present some joint work together with my co-authors Ford, Svensson, Erkre, Runesson, and Janicke. We're considering numerical model reduction, whereby we want to approximate the finite element approximation further by introducing a reduced basis. This is sufficient for multi-query problems typically, and the work I present today is inspired at large by seminal works on the application of micromechanics. The present study is ongoing work on viscoplasticity as a model problem. So we consider the equilibrium equation of the Cauchy stress sigma together with the evolution of viscoplastic inelastic strains, as you see here, where we have linear elasticity together with perfect viscoplasticity of Presuna type, as illustrated here. So U is the displacement field and epsilon Vp are the viscoplastic strains. We formulate this problem in a non-standard fashion by considering the mixed weak form where the displacements U and the viscoplastic strains are solved for monolithically. In the finite element setting, this means that the viscoplastic strains are typically discontinuous functions. The reason we do this is to accommodate the numerical model reduction scheme, which goes as follows. So the first step in an offline stage is to generate a POD basis for the viscoplastic strains. Thereby, we can write or expand the approximation as a set of spatial basis functions times temporal coefficients that we ultimately want to solve for. Using the nonlinear, non-uniform transformational field analysis approach, we can solve for the displacement field exactly a priori by parameterization with respect to external loads and the adopted basis for the viscoplastic strains. Adding everything together and using a Galerkin projection, we get the evolution equations for the coefficients of the viscoplastic strain approximation. And this becomes a discrete system, of course, where NR is now the number of modes that we have here to solve for. So considering a prototype problem, we have a beam-like structure where we apply loads in the vertical and horizontal direction at the endpoint. And for generating the basis, we consider two simulations with simple proportional loading only. But in the application example to come, we will combine these loads. So just to illustrate, we have a set of the first three basis functions in terms of viscoplastic strain fields are illustrated here together with the eigenvalue spectrum for the POD. And what we will investigate is, of course, the number of modes that we have to incorporate in order to get a good approximation. Looking at the application, we combine the loads using the sinusoidal functions, as you see here, and we plot the evolution of the relative error of the tip displacement in vertical and horizontal direction. And looking at the vertical tip displacement error, we see that for only one basis functions of viscoplastic strains, we have a large error of almost 60% as worst. We can also investigate the effect of the nonlinearity by comparing two different load amplitudes. And here I just show the convergence or lack thereof rather for the displacement error, the vertical displacement error at the end time on the left-hand side, and on the right-hand side we show the same thing but for the root mean square error of the effective stress. Finally, we also investigate the influence of the error on the underlying discretization, and in particular, as we increase the number of basis functions, then the error depends more and more, so to speak, of the underlying mesh. So to sum up, we have an efficient procedure for speeding up the analysis based on small strain kinematics and a suitable parameterization of the loads. The error depends on a large amount of variables, and it cannot in general be assessed by the POD spectrum. Therefore, future development concern the a posteriori error estimation for reliable error control. And in this case, based on the NTFA approach, we will use the fact that the residual resides only for the viscoplastic flow rule. Thank you for your kind attention.
Very good. With this nice presentation, we can go to the live discussion now. Feel free to simply switch on your video if you feel like that to make it less impersonal. And also to keep continuing asking questions in the chat or live as you prefer. So let's start from the first question. This is for Megan. Actually, he already answered in the chat, but maybe I think this is recorded and I'm not sure whether the chat is recorded too, so I will ask it. Sergio Lotnik, he asked, Megan, do you have some mechanism to keep concentrations bounded? For example, between 0 and 1?
No, here we just use the concentration of, we just use the actual percentage of the concentration, which is given from the industrial company. We don't have a direct mechanism in our modeling. But here we just have the results based on the experimentals which we have from our industrial company.
Okay, thanks, Megan, for answering. Now I think we have another question.
Yes.
No, I guess there was a mistake. There was, I'm not sure this was a question for you, Megan. Pedro Diaz wrote down that he made a mistake. It was to Ahmed, so I will ask it to Ahmed. Are you considering to use any post-processed error indicator to assess the quality of the solution and possibly to adapt the mesh?
Hello, thanks for the question. And thanks first for the attention. I
Hello,
didn't
Ahmed.
see this at the end of the presentation because of the 5 minutes limit. So thanks for listening. So if I understand the question of Pedro correctly, if you're talking about the post-processed error indicator, like for example, in HDG, we have the post-processed solution that can be used as an indicator for the error. So in my case, since I'm using the divergence-free method, the post-processed solution with the velocity that we get is not divergence-free, so we cannot rely on it. So I don't use it at all. So I lose the benefit of having a post-processed solution in my case. So I hope this answers your question.
Okay, thanks. Let's see if Pedro wants to ask something else. He will write it down. You have several questions, actually. So you have another question from, let me find it now, Fredrik Larsson. He says, do you foresee any problems related to transporting the XFEM discontinuities with the solution? Fluid interface, it means.
Yeah, definitely. There are actually many problems that come with this method, and is still under development. So, for example, I can see at the moment like two problems that I have in mind. The simplest one is now I'm solving only like academic problems. So as you can see from the examples, the way that the material interface cuts the elements are simple. So basically, I have a cut that goes through the element and divides it into two subdomains. So in more complex problems where the interface is moving, definitely we're going to have more complex cuts, curved cuts, and probably cuts that divides the element into more than two subdomains, so 3 or 4 subdomains. And they're like between like the two materials, air and water, in different parts. One more example that we can have is that we have one subdomain totally inside the element, like a small bubble maybe inside the element. That's the first problem that we might have. Definitely, we're going to have it. And the second problem, maybe even if the cut is simple and it divides the element into two subdomains, we can have very small cuts. So one subdomain could be like 1% of the whole element. And that leads to conditioning issues. What I see in the literature, what they do is that they go away from the motivation of this work totally, and they don't use one single fitted mesh that is fixed throughout the whole domain, but they change the mesh, they adapt the mesh. So maybe that could be the solution, but I haven't done this yet.
That's
so
great for investigation.
Definitely there are many other problems maybe.
Another question for you, Ahmed, from Ruben Sevilla. How do you plan to represent curved interfaces to ensure that you do not lose the high accuracy provided by high order models, elements? Sorry.
Yeah, that's actually a really nice question, and I have an answer for it, but I'm waiting also for for other answers and suggestions. And I was actually going to ask you, Ruben, about this. I have an email in my draft. So what I do at the moment is the following. Given a level set nodal values, like first we solve level set equation to get how is the interface cutting through the elements. So basically level set is like a sign distance function. So let's say at the moment, I just have those values, the nodal values, for how far the point or the node is away from the interface. What I do is in one element, I have the nodal values of the level set. So I approximate the level, the interface using polynomials of the same order of the element, or sometimes higher order. What I found in the literature, that the general case to represent any complex interface could be order 2p plus 1. So and it's simple polynomial approximation. Now comes the second part, or the second issue that comes with it, is now I have the high order representation of the interface. How do I get the modified quadrature in this in the two subdomains at least? So what I do is that I found this open source code called AlgoYM. I'm not sure exactly how it gets the modified integration quadrature, but probably subdivision, multiple subdivisions of the element. And it gives me the high order integration quadrature that I need. And the issue is that this code only works for quadrilateral elements in 2D and hexahedrals in 3D. So I cannot use it for triangles and tetrahedrals. And that solves my issue at this point. I'm interested actually in knowing how to do it in triangles and tetrahedrals, because I'm having other issues in quadrilaterals that might lead me not to use it. So I hope this answered the question.
Very nice. Actually, if Ruben wants to then discuss it with you, I guess.
That was a nice opportunity.
So this is yes. So let's see. You have another question, but maybe I will go on with the other speakers just to make sure that everybody has the chance to discuss it. Otherwise, I will go back to you.
Yeah, thanks.
Okay, so now we have a question for Philip. A couple of questions to Philip. The first one is, can you please elaborate on the nearest sampling point approach? Hello, Philip.
Hello. Yes, that's a very, very good question. I'm gonna share my screen to answer. So, is this okay? Yes.
Yes.
So, in terms of how the sampling is done, so when how the nearest points are selected. So, since the parameter is one-dimensional here, this is simply the Euclidean distance that I'm considering. So, for instance, here, if you have mu there, and the nearest points are in are simply based on the Euclidean distance here. So there's nothing really special here. But if the question is more on how we build these blue points, this depends on the problem that we have at hand. So typically, the problem that I shown is a double layer. So we take the kernel of the double layer. So this is here the expression there. And it depends on the distance between X and Y. And so basically the only variable that we are considering is the distance between X and Y, which is R. And this kernel can be split into a non-singular part and a singular part. And so basically to find the blue points, we simply work on the non-singular part here, using the locally adaptive strategy. I hope this gives an indication on how these blue points are built.
Okay, so Manisha maybe will let us know if that's satisfying for understanding what she wanted to know. I will go on with another question to you, Philip, from Frederick Larsson.
Yes.
Is there a potential problem that the basis is always enriched during the sweep? Could there be a benefit in coarsening the basis as you progress?
Yes, that's a very, very good point. Yes, because as the method works now, the reduced basis is always enriched, and it could be a good idea maybe to leave out the lower frequencies once we reach the higher frequencies. But so far we haven't tried it, but it would be a really good thing to try. Yes, to with the goal in the end to get the smallest possible reduced basis online. That would be a good idea to try.
Nice. So Frederick, thanks. Replies, she's a little bit confused. If the selection of points are near, wouldn't it lead to more coherency?
Coherency. So the points are near. Basically,
sorry, Philip. She says redundancy. She specifies
redundancy. Okay.
I don't know if you.
So basically, the dependency in mu, we can find it. It's basically taking only just the local, the nearest points will be enough to locally approximate the operator. And the experiments show that, in fact, we can actually take only the local neighborhood to get a decent approximation locally. But this approximation, of course, only works locally and cannot work someplace else. So this, yes, this is this I think answers the question. Yes.
Yes. So she understands now. Thank you, Philip, for your answers. To Gabriel from Bruno. And the question is, how would your data-driven model compare to the classical viscous models like Maxwell and Kelvin Voigt?
Okay, hello everyone.
To answer the question to Bruno, what we do is here is trying to estimate the values of the stresses. So how does it compare? Of course, not good in that sense. If you use a viscous model or whatever, in here, in my case, we're using a Zener model, which is basically one elastic branch and one branch with a spring and a dashpot. And yeah, it doesn't compare very good because we're not obtaining what is like a perfect solution that you could obtain with FEM. So in our case, the error, as you see, is in the range of the 10-20% error. But the thing about the method, the DDI, is that basically we can use it for two things, or to estimate the stresses, or to find the parameters that define the material. And in that sense, we are now in the phase of finding the estimating the stresses in viscoelastic, and the idea in the future work which we are actually doing now is find a way to retrieve the different parameters that define this material. Let me share a bit here.
Yes.
This is for another presentation I did, but basically this is the model that we're using. And the idea would be at some point to be able to come back to obtain these two values. So we can, because in this case, we can obtain the values of stress like this. And we would like to find a way to go from our curves or stresses estimated to go to this, to basically obtain these three parameters that we need to define our material. So.
Okay. Thanks, Bruno is satisfied with your answer. And actually, I wanted to ask you something also, Gabriel. Yesterday, we listened to a very nice talk from Professor Stefanie Rehse about data-driven models. And I was wondering, what is the main difference or the similarities with what she presented and what you are doing?
Yeah, for that, I will also share the current presentation, and let me find the slide. Yeah. Basically, in a sense, they are exactly the same, but a bit different. We are trying to solve exactly the same problem. And as you remember, she was trying to say that they were trying to find like the nearest neighbors. And that's basically what's explained here. The difference is that she called this a penalty function. We call it a distance norm, where basically we're trying to minimize the distance between points. The difference is that she starts by assuming that we know the material. She has all this database of values where she has already the strain and stresses that define the material from previous tests, and she could just retrieve what is like the displacement and the stress and strain in the current problem. We start by the basis that we cannot know that, and even more, we cannot even estimate properly the stresses in real life. We can do some approximations, but that's never like the proper case. So we start by saying, okay, we can perform some sort of imaging technique and we can obtain the displacement already. And we start by knowing the displacement. And of course, because of that, we know the strains. And that we put in the solver, and we want to obtain the values of the material states, which will basically be what defines the material in the end, like the curve that we can adjust in a sense. I mean, the idea of this method is always to not have to adjust anything. But technically, with these points, you can at some point adjust and obtain the proper or the typical values for a material. And of course, the estimation of the stresses in the samples that we have, since we only know the strains.
I see. Okay, thank you. Also, another question. You said that you presented some results. I was wondering, are these results kind of universal, or they depend on the cases?
Okay, the results, of course, are not universal. They depend a lot on the case. And again, in here, for example, I showed that the optimum amount of previous history steps is 10, but this is only because we have in this case, we have a particular value for the relaxation time. And in other results that I'm not showing here because of time constraints, this curve is basically dependent a lot on what type of force I'm putting to simulate the behavior of the material, and also what relaxation time the material has. So in general, this is just a percentage of the
or should be a percentage of the relaxation time of our viscoelastic material.
Okay, thank you, Gabriel. So let's see in the chat if I was missing. I think there was this question that I skipped, which was to Ahmed. So since we have some time left, I will go back to that. So Ahmed from Sergio, I understand that you want to apply the XHDG to transient problems governed by Navier-Stokes. If that is the case, do you expect to have issues in the description of the discretized level set in places with fluid vortex?
Yeah, I was just going to write the answer, but it's easier to explain it. So I see it's like the same question as Friedrich. But this case is one of the, I would say, the most complex situations if I have a fluid vortex or multi-fluid vortex. So I really haven't reached the point to start doing this, and I think it's not it will not be part of the thesis. But since this work has the objective of going into turbulent flows at the end, so I think this is going to be a really hard challenge, because when I think of it, at the end, I think this would lead to the idea of having mesh adaptation with very fine meshes to capture the resolution of vortices. Yes. And maybe higher order would help, because in terms of discretizing the level set, because we have many or more nodes inside the element, so that can help in capturing the level set if the interface cuts through the element like multiple times, or it has many subdomains inside the element. This is my intuition about it, like when I think about it, but really I haven't studied it. But it is going to be a massive challenge. Yeah. Thanks. I hope I answered the question.
Thank you. Thank you.
And thank you, Fabiola, for the
seems like that
for the coordinating.
No problem. No problem. So let's see. I think I've asked all the questions from the chat. Is there any other question from the audience? Let's see. Or is something that the people who presented the work would like to add? Seems like not. I actually have a couple of curiosities. Maybe I can just ask them. One is to Fredrik Larsson. I'm not really familiar with this topic, but I was wondering if the model which was presented, it's something that can be used on the macro scale, on the macro and micro scale, or I don't even know if it's a good question, this one, but I was wondering if there is some possibility of multi-scaling approaches. Maybe I'm not sure whether Fredrik is listening to me. So I will ask the other curiosity I had. This was for Philip. Philip, can you hear me?
Yes, yes.
Okay, thank you. I wasn't sure if it was my connection or really a curiosity. You stated at the very beginning in your introduction that an application in the aerospace industry is to study the noise generated by the aircraft, right? With this problem. And I was wondering, what do you mean by noise? Do you mean the noise generated? So what does it affect? The structural behavior of the aircraft? We are talking about noise in the sense of environmental noise. Are we talking about noise for the passengers? That was just a curiosity in that sense.
Yes, it's the noise generated by the reactors. And this is usually a broadband noise, which ranges a lot from low to high frequencies. And so in order to simulate that, there's really a need to explore all these frequencies. So the work that I've presented is the first step to try to make this such frequency sweeps. And yes, this is of course something that the aerospace industry is interested in, to study the broadband noise generated by aeroelastic structures, for example, also.
Okay, thank you a lot, Philip. This was a curiosity. So I'm reading that maybe Frederick was speaking, but we could not listen to him, but is answering on the chat. So the method is very useful for multiscaling. This has been the most targeted application in literature. Okay, thank you a lot, Frederick, for your answer. No problem with the connection. Okay, if nobody else has further questions, I think we can close now the session. I will show you this slide. Okay, so as you can see, now we have a break. Enjoy your next session, fictitious domain, methods and application. Thank you a lot to everybody for participating, to the speakers and to the audience. I hope you enjoyed the session and enjoy the rest of the conference. Thank you a lot.